Post-INN, Visual Post Regression and Localization with Invertible Neural Networks. The visual post regression problem is to find the 6-degree freedom camera pose by training a neural network on a set of images taken within the same environment. The initial attempt, PoseNet, uses a convolutional encoder, average pooling layers, and linear layers to regress poses from images. After that, the field had made incremental improvements by trying different architectures, better optimization methods, etc. Recently, there was a 50% leap in the accuracy of pose regressors by using NeRF to render synthetic images at novel camera poses. However, the state-of-art either uses high-resolution images, which takes a long time to prepare, or uses direct feature matching methods, which require NeRF image rendering during the localization process. In this paper, we propose a new approach to the pose regression problem, that is, to view it as an inverse problem and solve it with invertible neural networks. This paper has 3 contributions. We formulate the pose regression problem as an inverse problem. Using invertible neural networks, INNs, we realize a pipeline for fast data preparation and training. We validate our approach on common benchmark datasets. The performance is on par with the state-of-art despite a much simpler structure. We also demonstrate uncertainty estimation and efficiency of our method by deploying it on a real mobile robot. Let's start from the first point. We can view the pose regression problem as an inverse problem. The forward path is from camera poses to images, and the reverse path is from images to camera poses. With a trained NeRF model, we can render photorealistic images from novel camera poses. That means we can sample the image space by sampling the camera pose space. Now, if we can sample both distributions, then the pose regression problem is reduced to finding a mapping between the distribution of poses and that of images. A normalizing flow is suitable for this job, which is a series of invertible transformations, such as coupling layers, for learning bijective mapping between 2 distributions. To form this transformation, we need to match the dimensions of camera poses and images. INNs require the input and output dimensions to be the same to ensure the invertibility. Therefore, we use a VAE to encode the input image. The encoder of the VAE consists of a pre-trained EfficientNet B0 backbone, an adaptive average pooling layer, and 2 separate linear layers for mean and variance terms. In the decoder of the VAE, there are in total 12 layers of convolutional and transconvolutional layers to recover the image. On the camera pose side, we use positional encoding to augment the dimension of the poses. A latent space following normal distribution is concatenated to the encoded image to capture the ambiguous information when training this bijective mapping. During evaluation, we can batch evaluate the reverse process of pose-INN with sample latent space Z to reveal the full posterior distribution of poses given an input image. The conditional input is not used for absolute pose regression tasks on public datasets and is only used for real-world experiments. To optimize this network, we use loss functions from both sides. We have L1 loss on the encoded poses and encoded images. We optimize a elbow loss for the VAE. The network is trained altogether. In order to learn this mapping, we need to sufficiently sample both distributions. We train a NeRF factor model with the training dataset and render 50K 160 by 90 images for each scene at sampled camera poses. The sampling pipeline for representative camera poses is also key to this method. Details can be found in our paper. Since we only use low-resolution images, this data preparation process only takes around 1 hour on a single GPU. We validated our method on Cambridge Landmark and 7 scene datasets. You can see that our performance is on par with the state-of-art. We also compare with them from other dimensions. Our method only requires low-resolution renderings, which can be done offline. Pose-INN is not only accurate but also very efficient, which makes it suitable for an embedded platform. To show that, we deployed it on a Jetson Xavier NX board. We then did a localization experiment using the F110 card, which is equipped with a 2D LiDAR, RGB camera, and the Jetson board. We ran particle filter localization with 2D LiDAR for training data mapping and ground truth. For 2D localization, it is usually done with the prior knowledge of a rough starting pose for the robot. So we use a conditional input that takes in a rounded value for the robot's previous pose. This essentially reduces the ambiguity of the inverse problem. Please see details in our paper. We did 2 experiments. As you can see, our method gives accurate results even if the training trajectory does not fully cover the test trajectory. Last but not least, post-INN outputs a distributional pose during the evaluation by sampling the latent space of the INN. We can use the variance of output poses as an uncertainty estimation. Here we use a EKF to fuse the output pose with the odometry of the robot. We can also show the use of uncertainty estimation on public datasets with output filtering. Here we present the average value of output poses on the left, and on the right we filter poses based on the median value of the variance. We can see as extreme values get filtered, the average errors are greatly improved. To summarize, post-INN is an efficient and accurate method for visual pose regression with uncertainty estimation. The results are on par with the state of art on public datasets with clear advantages. The data preparation and training is fast with our proposed camera pose sampling pipeline. When deployed on an embedded platform, post-INN delivers centimeter-level localization while running more than 150 Hz. Thank you.